Alright, what's up people? Welcome back to another video. Today we're going to be looking at, super quickly, converting our delta hydroxy acids into delta lactones using cyclization, okay, or direct cyclization. This looks scary. It really isn't. It's pretty straightforward as long as you stick to numbering things when you have cyclization. That's typically the thing that trips up students. So, over here we have our delta hydroxy acid, okay, and your alpha, beta, gamma, and delta carbons are labeled, okay. Make sure I'm using red here. Perfect. So, step one. What's going to happen is you have a lone pair of electrons on the OH group on the delta carbon. So, hence the name delta hydroxy acid. Okay? What's going to happen is, and this is the thing that really confuses people, is you're going to have these lone pairs attack the carbonyl of the carboxylic acid. So, let's draw an arrow from these lone pairs to this carbonyl. Okay? There are numberings. I'll get into that in just a second. But right now, let's just draw that. Okay? We can draw it looping up this way, but I don't want to make things cluttered, so we're just going to show these lone pairs attacking this way. When we do that, what is going to happen? You're going to have more than 5 bonds on carbon. Something needs to break, and again, the theme here, you'll notice if you've watched these videos in order, is that the most susceptible bond that's going to break here, in this case, is the C double bond O, so these electrons are going to break and collapse towards the oxygen. Great. Now, you're going to have a ring form, just based on you have one end of a molecule attacking another end of the same molecule. So that's sort of like these things are snapping together and you're forming a ring. So notice a ring, okay? In this case, it's going to be a 6-membered ring. How do I know this? I'm going to start numbering from the lone pairs on the oxygen, this OH over here on the delta carbon, so this delta carbon, and we're going to number from we're going to label that one number 1, and we're going to move across until we get to the part where those lone pairs of electrons arrived. So we have number 1, okay, for our OH. Number 2 for this delta carbon. Number 3 for this carbon. Number 4. Number 5. Number 6 is where the lone pairs were sent to or attacked, correct? Perfect. So we're going to form a 6-membered ring. Now, let's redraw everything and just pick a carbon and start assigning these numbers that you gave it, right? So in this case, I chose to move counterclockwise. So I went 1, 2, 3, 4, 5, 6. You could have very easily chosen 1, 2, 3, 4, 5, 6, and so on and so forth. The reason I'm doing this whole numbering thing is because this now enables you to, for example, let's actually just erase this. So as a proof of concept, let me erase this. Where's the black marker? If we erase this, right, in the exam, you might be asked to show this mechanism. You're going to be like, okay, well, what the hell am I supposed to draw? So that's why the numbers come in. Let's draw our, step 1, let's draw our 6-membered ring. Our 6-membered ring, this is not the good marker. Where's the good marker? There it is. Let's draw our 6-membered ring. Perfect. How do I know it's 6 members? Well, 1, 2, 3, 4, 5, 6. If you're doing this course by now, I'm sure you already know what a 6-membered ring looks like. Perfect. Now let's assign the numbers that we just did in the step before this. So let's use a different color. Let's use green. So you can choose clockwise, counterclockwise, doesn't matter, up to you. As long as you pick a direction and stick to it. So we have 1, 2, 3, 4, 5, 6. In this case, I've gone what? Clockwise. Okay. So now let's go. Matching number 1 with number 1 and seeing if there are any groups that need to be on that carbon or on that or where that number is. So number 1, what do we have? Well, we have an oxygen with a hydrogen attached to it. So let's go ahead and erase this and draw an oxygen with a hydrogen attached to it. OH. And there's going to be a plus because oxygen has 3 bonds. Let's go ahead and add number 1 here again. Perfect. So on carbon number 2, what do we have? Carbon number 2, we're going to have an R group. Perfect. Let's go ahead and draw our R group. On carbon number 3, we have nothing. On carbon 4, nothing. Carbon 5, nothing. Carbon 6, now, we are going to have an OH group. So, you're going to have 2 groups. Let me just... You have an OH group, this group. And now we went from a C double bond O, we broke the double bond, and we formed a what? CO minus. That's it. That's it. That's why I did the numbering thing. That's why it makes life so much easier. The second you understand how the numbering thing works, you just get your 6-membered ring, you get your numbers clockwise, counterclockwise, makes no difference to me, and then start making, assigning where each group is, and proceed with the rest of the mechanism or the question. So, the next step here is we have this O minus. We have this O minus. Well, what's going to happen is this O minus will now deprotonate in a weak acid in solution, or we just have HA, some sort of proton donor. Okay? This is going to become A minus. We don't really care about that. All we care about is that we're going to have what? We're going to have OH here and OH here. As you can see, it looks like something changed. It looks like the compound flipped. No. When I was first setting up this example, I drew the numbers in counterclockwise, if you're paying attention. Here it's in clockwise. So the question is correct. It remains exactly the same. What happens is this just looks flipped. So that's why it might be a bit confusing. You know, in hindsight, I should have just stuck to the same numbering. But again, it's just the numbering, clockwise, counterclockwise, makes no difference at the end of the day. Okay, and if you want, do it on your own as a proof of concept. And if you get anything wrong, by all means, comment something or let me know. So we're going to have our two OHs here, our R group, and our OH plus, OH plus. Perfect. Now, the next thing that's going to happen is one of these groups, remember they're both OHs, so it doesn't really matter, is going to remove this H that's attached to our O right here in the middle, right? So you're going to have, you can pick either one. In this case, I'm going to pick this bottom one. It's going to remove that H. When you remove that H, these electrons will collapse towards oxygen. Perfect. When that happens, we now have our OH group. Perfect. We have an OH2 plus group. How did that form? In the previous step. When that happens, oh, and of course we have our just oxygen with the two lone pairs. So those two lone pairs, perfect, from the previous step. The next thing that's going to happen is we want to kick out this OH2 group. The best way to kick it out is, well, this OH group that doesn't have an extra hydrogen will build a double bond and kick out this OH2 group. Why is it going to kick out the OH2 group? Because remember, if you build a double bond here, this carbon right here, this carbon can have a maximum of 4 bonds, or all carbons really, can have a maximum of 4 bonds. If you build this bond, you're going to have to break something, because in that case you'd have 5 bonds. What's the most susceptible bond that's going to break? This one. Or rather, this bond which holds the OH2 group. Sorry. What's going to happen next? Perfect. What's going to happen next is you're going to end up with your C double bond OH, C double bond OH. This H is here, this H is here. You're going to have a plus on that carbonyl, because if oxygen has 3 bonds, again, I'm repeating myself here, but if oxygen has 3 bonds, it's going to have a charge of +1. Now, we just kicked out what? OH2. What is OH2? Basically water, H2O. So we just write it above this arrow over here, or this reversible reaction arrow. What's going to happen next is the lone pairs on the oxygen from the H2O will attack this hydrogen. They will strip that carbonyl of its hydrogen, and these electrons, the electrons in this bond will collapse towards the oxygen. And you end up with your delta lactone. Not rocket science, and plus H3O plus, your acid that you just formed in this step. But again, we don't care about that. It is not the major organic product. So as you can see, it's pretty simple, very straightforward. The only thing that tends to trip up people is when they're solving these questions is, what the hell the ring is going to look like. Is it going to be a 6-membered ring? Is it going to be a 5-membered ring? How am I going to know what it is? And the best way for you to do that is, of course, by numbering. So number where the lone pair is, right? So what atom has these lone pairs, and where is it going? Okay? And that final point, the last atom that it touches, is now going to be your last atom that forms the ring. Okay? Yeah, I don't really think I have anything else to add more than this. Like, comment, subscribe, dislike it if you disliked it. Good luck, people. Woo! All right.